last day I was discussing about radial basis function interpolation technique for the differential equation. So far, yesterday I have not touched differential equation. I was there only at the radial basis function and how with the help of radial basis function we can interpolate the data. In the earlier definition, there were two parts, one for radial basis, another for polynomial. And why the polynomial part was necessary? Because that will ensure the existence of non-singularity of the matrix. But for the simplicity, I am going to take only radial basis part, because we are familiar with how to interpolate data based on polynomial. So I will concentrate on radial basis function only, but in the similar manner, we can proceed for both radial basis function plus a polynomial. So here I have taken a differential equation d2u by dx square equal to function of x, u and du by dx. This is basically a non-linear differential equation, but for the time being, all of you please take that our differential equation is only d2u by dx square equal to function of x. Very simplest form of second order ordinary x square equal to f of x only. Now, our domain is A to B. I have divided this interval A to B into several parts that is denoted by xi, and I is going from 0 to L plus 1. Now, I have a Gaussian radial basis function that is psi r equal to e raised to the power minus. I have told you it is basically c square r square, where c is the same parameter. Now, our aim is, with the help of this radial basis function, we will construct a discrete scheme. What kind of discrete scheme we will consider, that I will explain later on, and what is the beauty of that scheme. Everything will be explained later on. But for the time being, just take a function r naught. R is basically our psi, is the radial basis function. R naught is e raised to the power minus c square x minus x naught square. If you are having any confusion in x naught, where does this x naught is coming? For the understanding point of view, just take r naught is x naught is 0. Similarly, I have defined r1x, where the point x1 is appearing. Just take x1 is half. In r2x, I have taken third point x2. You take 1. So I have basically function like e raised to the power minus c square x square. Another is e raised to the power minus c square x minus half whole square. And the third one is accordingly. The three functions are on the same line of pattern, except I have changed x0, x1, x2. Now, there are three functions. All are having similar character, exponential function. Now, I am going to denote, this is just a symbol. Symbol x1 is equal to x0 plus h. That is, x1 is a point which is next to x0 towards right hand side at a distance h. Please do not go on the numbering 1 and 2. This is just the easy in writing. x2 is a point which is left to x0 at a distance x. So I have basically, I am sending a photo on the WhatsApp again. Just look at this graph. Is this convenient to you all if I am sending on the WhatsApp, because there is no other way? Is it okay? Please see, there is a simple nomenclature of the points. I have written a straight line because I am discussing one-dimensional problem. So I have a straight line, and there is a point x0 that lies in between. and x1 is towards the right and x2 is towards the left. So basically x1 is our xi plus 1 because it is next to x0. X0 is basically, in practical, it is xi, and left side it is xi minus 1. So mathematically here I am writing x0, x1, x2, that stands for xi plus 1, xi plus 2. Now, if I take I equal to 1 in actual notation, then we will get x0, x1, x2. If I put I equal to 2, we have points x1, x2, x3. Similarly, I equal to 3 will give you x2, x3, x4. So basically, we have a sliding window pattern kind of things. We have 3 points here, then next time 3 points here, then next time 3 points here, and so on. So by this way, this sliding window technique kind of things, we can cover whole the domain just by changing values of I. So with this help of 3 points, I am telling you why I am taking 3 points only. I will explain later on, but for the time being, just wait. I have taken only 3 points for calculation of, for finding approximation of first order derivative at the point x0. So this is what is first derivative? Simply dr0 by dx at the point x0. So it is written as x equal to x0. And this is a linear combination a00 r0. A00 is again a parameter that will be determined later on. R0 x0 R0 x0 plus A01 R0 x1 at the same radial basis function at another grid point. Another grid point is next to x0, and plus A02 R0 x2. So basically, in the first equation, what I did is I have taken a linear combination of radial basis function values at different points. Similarly, exactly on the same line, I can have another relationship dr1 by dx at the point x equal to x0 with the same relation, except r0 is changed with r1. Coefficient remains same. This coefficient A0, A00, A01, A02 are called weight functions. Next, exactly on the same line, dr2 for the third radial basis function, I have kept weight exactly same as and replace the radial basis function r2. Evaluation at the point x0, x1, and x2. Now I am having 3 equations and 3 unknowns. These 3 unknowns are A00, A01, A02. Can be calculated. Now, when you R0, R1, R2, everything is known to you. You can find the derivative. When we find the derivative, we have these 3 relationships. Last 3 lines. This is a simple mathematics. Can be easily written in this form. Next. I can write these 3 equations in this matrix vector notation. Now, just look at the coefficient matrix. Coefficient matrix, I can write Q equal to 1 xi raised to the power 4, xi 1 xi raised to the power 4, xi raised to the power 4, 1. Where xi, I have just make a notation e raised to the power minus c square h square. For that, I have written xi. Just look at, before finding these values weight, you have to see whether this matrix is invertible or not. So I am going to find determinant of Q, and it is coming out to be xi plus 1q, xi minus 1q, xi square plus 1. and determinant is 0 provided xi equal to plus minus 1 or xi equal to plus minus I. Xi equal to 1 is possible if c is 0. Xi equal to minus 1 is not possible for us, and xi equal to plus minus I, which is not belonging to R, is also not possible for us, because I have taken c is a real number, positive real number. So in our case, this coefficient matrix is a non-singular matrix and can be invertible. This is the inverse of this matrix exists. Please note that this is not a single matrix. Basically, this again moves on the sliding window. So this is for the 3 points x0, x1, x2. In the next time, when the computation starts, next time it will go for x1, x2, x3. Again, in the next time, it goes to x2, x3, x4, like this. So this matrix is invertible in each case for calculation of this weight coefficient. Now, next question. So I can say that C is greater than 0 and Q inverse exists, and I have got the value of A00, A01, A02 as this value. Now, I have started with the linear combination A00 R0 X0. That is basically the value of U at X0. R is basically the interpolating polynomial for the function U. So R0 X0 is basically U0. Similarly, here I am coming back. Here I have written the first line. Here I have written R0 X1. R0 X1 is basically U1. R0 X2, value of R at the point X2 is basically value of U at point X2. So the first derivative du by dx at X0 is basically this relationship A00 U0 plus A01 U1 plus A02 U2. I have written the symbol of approximation because this is not exact. I have obtained via some approximation. That is why it is that is why it is approximate. Just look at right hand side of this approximation. I am going to apply the Taylor series. That is, all the values of A00 is known to you, A01 is known to you, A02 is known to you. Just substitute everything here, right hand side. And what is U0? U0 is basically A00 is, I think, 0. So yeah, A00 is 0. So the first part gone. A01 I have kept here. U1, for U1 I have written U at X0 plus H, and U2 is basically U at X0 minus H. Just expand it with the help of Taylor series. These two terms, U at X0 plus H and U at X0 minus H, you will find, please note the right hand side, it is U first derivative plus some terms that consist of H square, including same parameter C plus order H4. In the nutshell, I can say that this quantity is basically first derivative of U at X0 plus order H square. So this radial basis combined with finite discretization gives a second order approximation of first order derivative. I have calculated approximation of derivative at X0. Although I do not need approximation of derivative at left and right nodes at this point of time, but I am going to calculate here itself because it is on the same line and it is easy for you to understand. Before proceeding to further, I would like to tell you, I have taken only 3 points, but it is possible to take 4 points, 5 points, 10 points, as many points you wish. Absolutely, there is no problem. There are authors who has considered all the endpoints of the domain for discretization technique. But my aim is to use the minimum number of points to discretize. I'm just trying to understand, this is the general understanding. Suppose I'm telling you, you are finding first derivative. Then how many points is required for you? Du by dx is basically limit h goes to 0, u of x plus h minus ux whole divided by h. This is our general formula. So how many points you have used in this formula? One point is x, another point is x plus h. So 2 points are required to calculate first derivative. 2 points are required to calculate speed. Yeah. Next, second derivative, acceleration. Acceleration is basically you need at least 3 points, then only you can compare the first 2 points and second 2 points. Second derivative, the formula known to us is d2u by dx square equal to limit h goes to 0. In the numerator, it is u of x plus h minus 2ux plus ux minus h divided by h square. This is what your second central difference operator. So for finding second derivative, we require at least 3 points to evaluate it. The question is it possible to calculate second derivative with the help of 4 points? Very much possible. With the help of 5 points, very much possible. But if you increase number of points, because we are on the sliding window, if we increase the number of points, suppose you have calculated the second order derivative on 5 points, then in the last you will see you will achieve a matrix which has 5 diagonals. If you are using only 3 points, you will have matrix with 3 diagonals. Fortunately or unfortunately, we have so many mathematical theory from the functional analysis that describe the matrix with 3 diagonals. Stability or irreducibility or monotonicity or positive definite. I am talking of the matrix whose entries are not a number. That entries can be the function. In that case, proving a matrix is monotone or not is a difficult job. If the entries are some real number or some complex number, you can at least determine monotone or not, or irreducible or not. But in case when the entries of a matrix are function whose values are not known to you in advance, then it is difficult for you to obtain these properties. How can you find whether the matrix is positive definite or not if the entries are some function of x whose nature is not known to you before? So, but for the 3 diagonals, that is for the tridiagonal matrix, some theories are ample theory, not some, ample theories are available to us. But for 5 diagonals, for 7 diagonals, it is difficult. So that is why we are restricted to 3 points. This is number 1. Number 2, we are restricted to 3 points because of efficiency in computation. We are bound to have 3 points only, although it is possible to discretize it more than 3 points. Now, so this is what I have discussed, that the first order derivative is giving you second order approximation at the point x naught. Now we are going to find RBF approximation for the first order derivative at the neighboring points. That is, neighboring nodes are basically x1 and x2. Neighboring nodes of x naught is x0 is towards the right and x2 is towards the left. So here exactly on the same line, exactly on the same line, I will write here dr naught by dx at x equal to x1 equal to a10 r naught at x naught plus a11 r naught x1 plus a12 r naught x2. Please note these three weights are different from the earlier weights. The value may be same, I don't know in advance, but it must be different because I am calculating RBF approximation at another point other than x naught. So that is why I have changed the notation here. I have written left side 1, a10. Left is 1, stands for 1. Similarly, there is another equation for the another RBF function dr1 by dx at x equal to x1 h a10 r1 x naught plus a11 r1 at x1 plus a12 r1 at x2. The third equation is dr2 by dx at the point x equal to x1 equal to a10 r2 x naught plus a11 r2 x1 plus a12 r2 x2. Now I am having another three equations with three unknowns. I am not going to show you whether the matrix is invertible or not. In fact, you can check it yourself. But finally, I have got the value. These are the value. So with this value, with these values, I can have an approximation of u first derivative, which I have denoted by u bar prime. Bar just stands for approximation. Bar, wherever bar or tilde is appearing in this presentation, please take it as an approximation. This is not exact. So this is a10 u0 plus a11 u1 plus a12 u2. And this is also, although I should not write here order h square because I have to derive the Taylor series expansion on the same line the way I did earlier for approximation at x naught. This can also be proved that the approximation is second order. All right. So I have calculated first order derivative approximation at the neighboring point x1. Next, on the same line, I am going to calculate approximation at the point x2, and you will find it is basically a20 u0 plus a21 u1 plus a22 u2, and the values of these weight coefficients are coming out to be like this. So far I have calculated first derivative, approximation of first derivative. Although at this point of time I required approximation at x naught only, but these two approximation at x1 and x2, keep it for the record. Now our differential equation, I told you our differential equation is basically d2u by dx square equal to simple function f of x. So this differential equation consists of second order derivative and the function. So how to calculate RBF approximation for the second derivative? So this is what I am saying. We shall formulate 3-point Gauss radial basis function approximation to the second order derivative at the central node, at the node x naught only. I am going to calculate. I do not require approximation at x1 and x2. This is obtained by formulating the linear combination exactly on the same line. Earlier, I have used first derivative of r. Now I am going to take second derivative of r. So it is d2 r naught by dx square at x equal to x naught. I have used another weight coefficient a30 r naught x naught plus a31 r naught x1 plus a32 r naught x2. Radial basis function r naught at three different points in a linear combination. And another two equations are for another radial basis r1 and r2. So I am having three equations. Just simplify it. Xi is same as before. I have got this matrix. Earlier, I have shown that the coefficient matrix for first order derivative exists, but for the second order derivative, you have to show whether inverse exists or not. So it is easy to verify that this matrix is again non-singular. I think probably both the matrix are same coefficient matrix, but I'm not sure, you can check it. But it is non-singular for C greater than 0 exactly on the same line of pattern. Is it okay? Now I am available with the approximation of second order derivative. These are the values of A30, A31, A32, and the approximation of second order derivative is written as u bar double prime at x naught is equal to A30 u0 plus A31 u1 plus A32 u2. And this is coming out to be order h square, exactly on the same line. Now, I have a formula. I have calculated a formula earlier. U bar single prime. If you take limit c goes to 0, I am not talking of c equal to 0. C in the limiting case, it is coming out to be ux naught plus h minus ux naught minus h by 2h. I assume all of you are familiar with this formula. This is simply 2 mu x del x u at x naught. Mu is your averaging operator and delta is your first central difference operator. So in the limiting case, when c is going to 0, our approximation is basically reducing to the twice multiple of averaging operator and first central difference operator, that is mu and del. Any question? I am not going to take c equal to 0 in the computation, because the moment c you take 0, the computation may not work. I am not saying it will not work. May not work because of the inverse of the coefficient matrix in the first order and second order RBF approximation. So you must avoid c equal to 0. C must be positive. All right. Any question, any query? Well, very interesting. Next, same way, I'm going to take limit c goes to 0 in second derivative approximation u bar double derivative, and this is coming out to be u at x naught plus h minus twice u at x naught plus u at x naught minus h by s square. And this formula is nothing but the second central difference operator of u at x naught. So this is something which is known to us in the RBF. I have simply generalized it, and the RBF I have taken is without polynomial. In the same way, if you insert polynomial of degree 2 or degree 3, still you get similar result when you take limit c equal to 0. I have checked it for polynomial of degree 1, 2, and 3. I assume, I don't know, but I assume it also works for higher degree polynomial. But because I have not seen anywhere result, that is why I can't say with a confidence. But degree 1, 2, 3, 4 is fine. That is much more enough. So I am having the formula, two formula, u bar single prime and u bar double prime. I have as of now the approximation RBF approximation of first derivative and RBF approximation of second derivative. Now I am going to define two operators. Operators is a beautiful tool in mathematical science. I am telling you, it helps a lot in writing such a big thing in a small form. I am just going to write this f of x. Not f of x, it is fx u at x naught is nothing but I'm going to define h into u bar prime at x naught. This is just my definition for my easy understanding, the way of easy writing only. Sx is h square u bar double prime. So I have defined two operators. Basically, why I have multiplied h and h square is because you see in the previous slide here it is coming out to be in the numerator, it is coming out to be h. Here it is numerator, it is coming out to be h, and here it is h square. So when you multiply in the formula h and h square, then it is easy for you to apply Taylor series expansion at h equal to 0. But if you keep h square or h as it is, then you cannot apply Taylor series expansion. What I will do is later on in the numerator I will apply Taylor series and I will separately divide by h square. If you jointly take all these terms, numerator and denominator, then it is difficult for us to apply series expansion. So this is just for our easy understanding and ease in the calculation. So these two operators are basically coming out to be h u prime x naught plus order hq. Please note that in this line here there is no bar on u. This is because there is no bar, because I have expanded u bar prime. When you expand the right hand side, then you get h into u prime plus order hq. Similarly, here in the Sx, here I have got u double derivative at x naught. This is not u bar double derivative. U bar double derivative is basically the expression a30 u0 plus a31 u1 plus a32 u2. When all the values are known to you, you expand it. When you expand, you will get this quantity plus order h4. So you are having basically two equations, f of u equal to something, s of u equal to something. From these two equations, we will calculate first derivative and second derivative. This is what? Just divide both sides by h, you will get this one, order h square, because they are in the previous slide it was order hq, here it was order hq. To divide both sides by h square, it is coming out to be order h square. Very interesting. The approximation of first derivative and second derivative using radial basis interpolation is giving you same level of accuracy, order h square and order h square, same level of accuracy, what we have done traditionally with averaging operator and central difference operator. Well, I am telling you, enhancing accuracy is one of a big challenge for all of us. So here, these two operators basically giving you second order of approximation to the first derivative and second derivative. And more interesting is these two operators uses only 3 points for the RBF approximation. And this is nothing but in the limiting case is the combination of forward difference operator, backward difference operator, averaging operator, and central difference operator. Any question? Any query?
No, sir.
Now, you tell me, when you have derived an approximation of second derivative, then this differential equation, now come to this differential equation, d2u by dx square equal to f of x u du by dx. Simply replace d2u by dx, simply replace d2u by dx square by this relation. Is it okay? F is as it is f, x is basically x naught, because I am talking about at a particular point x naught. U is also at a particular point, can be written as u at x naught, and du by dx is replaced by this 1 by h f of u at x naught, because both the operators, these are giving second order accuracy, so it is plus, I have written plus order h square. Not only these two operators can solve the most nonlinear form, function of x comma u comma du by dx comma d2u by dx square. You take everything in f equal to 0, that can also be solvable using these operators. And such type of operators for solving the non-linear equation on a non-uniformness are called supraconvergent scheme. Here it is uniformness, so it is just a second order scheme. But in case of supraconvergent, the order may reduce. Here it is order h square, we may have order h only, but that has another added advantage. Maybe the order is less, but that is more suitable for the problems with boundary layer characters. So this is equation, I think I'm not seeing whether this equation is numbered 8, because the right hand panel is appearing here. Is it this last, this equation is equation 8? Is basically a system of equation, because I told you x naught, x0 is just our notation. X0 stands for xi. I stands for, I is going from 1 to up to L or I, whatever I have taken, as many points you have taken. So for different values of I, you are having a different set of different equations. So you are basically getting a matrix form of the nonlinear equation, and you can solve it nonlinear equation as usual. We frequently use Newton-Raphson method. There are other methods also that can be used. Nowadays there are so many modules which is available on the Python library, that can also be directly applied. Python, I suggest better to use Newton-Raphson method. That is the most reliable one. And in case of if f is linear, we will apply Thomas algorithm, or you can use Gaussian or Jacobi or whatever linear, iterative or direct method, whatever you wish. So by this way, till now, with these available operators, I can solve a most general form of nonlinear equation of second order. Now, this I am going to extend this method to the higher order method. These operators are used to calculate, to enhance the accuracy. Please note that here in this equation, I have got order h square. Well, order h square is taking much more computing time, or in order to have desired accuracy, you need to put much more grid points. So in order to reduce this complexity, we are going to enhance the order of this scheme. So our aim is to enhance it by this. Now, at this point of time, again, I am telling all of you, I am having a differential equation d2u by dx equal to f of x only. From this slide, your differential equation, keep it in the mind that it is d2u by dx square equal to f of x. First of all, I will formulate high order scheme for the simplest form of second order equation, and then based on that, I will extend it to the bigger equations. So, see, I am just going to denote f0 equal to d2u by dx square at x equal to x naught. This is basically same thing, f of x equal to d2u by dx square. I have just kept the symbol 0 as a subscript to denote value at a particular point. Is the first line is clear to you what I mean to say? It is f of x equal to d2u by dx square, that's all. Now, so what will be the first derivative of f? This is what I have written, f of x, that is d3u by dx cube. And f of x is nothing but df by dx. Of course, at x equal to x naught. Similarly, f naught xx is d4u by dx4 at x equal to x naught equal to d2f by dx square, of course, at x equal to x naught. At this point of time, if I am telling you what is the radial basis function approximation of df by dx, you can straight away answer this is equal to a01 f0 plus a02 f2 plus a00 f0 plus a01 f1 plus a02 f2. Isn't it? Same way the radial basis approximation of u first derivative I have calculated. Simply replace u by f. So df by dx you can calculate u d2f by dx square. You can also write radial basis approximation in terms of d2f by dx square is actually a30 f0 plus a31 f1 plus a32 f2. Is it okay? So three quantities are available to us: f0, f0x, and f0xx. Using these three quantity, I am going to formulate a linear combination. Linear combination looks like this: t equal to h square multiple of f naught plus h p1 f naught x plus h square p2 f naught xx. You may have a question why you have taken such a weird linear combination. Linear combination can be simply some multiple P0 F0 plus P1 Fx plus P2 Fxx. Fine. Listen, just look at this. Is again for my convenience in the calculation, because these leads to huge number of huge length of calculation. So you have to begin in such a way that in the later stage we are having less confusion. This is just for the convenience only. Here I do not mind if you multiply f naught by p naught, but suppose p naught is 1. Here h is multiplied with fx. Why I have taken h? What is this f naught x? F naught x is basically df by dx. Please recall, in df by dx, the denominator is appearing with h. In the limiting case, it is directly evident that in the denominator it is coming out to be h. So when you multiply h and h, numerator h and denominator h will cancel out. Similarly, f0xx, in the limiting case, you can visually see that in the denominator h square is appearing. So if I before multiply h square, that will cancel out. This is evident in limiting case, but in case of RBF, you cannot visualize it directly sometimes. So be careful. If you would like to visualize, you have to expand it. When you expand, then you can easily see it, whether h square is appearing or not. So, and here I have h square multiplied throughout. H square multiplied throughout. Again, there is a question why I am multiplying h square throughout. But just excuse me for the time being why I have multiplied h square. Can anyone give me the idea why I have multiplied h square again throughout? Actually, see, f naught xx is basically, this is du4 by dx4. It is fourth derivative of u. F is basically nothing but the second derivative of u. So f naught xx is fourth order derivative. So fourth order derivative, as you have seen, in the first order derivative, it is division by h. In the second order derivative, it is division by h square. Similarly, in the third order derivative, you will have division by hq. In the fourth order, it is division by h4. So actually, this is u fourth derivative, and when we multiply throughout by h square, this is coming out to be, the last term is coming out to be h4. Is it clear to all?
Yes.
Yeah, so with this linear combination, we will proceed further. With this linear combination, we will proceed further. Now, here f naught is d2u by dx square, and d2u by dx square can be obtained from the operator s at su x naught. So su at x naught, expand it, put it in this relation, Similarly, for the first derivative f of u x naught, although f of u x naught is not required at this place, but it is better to put it. So you are having basically two equations. In the previous slide, I have told you here. In this relation, you are having f of u and s of u. So these are the two relationships. I have expanded here up to h square only in both the equation. You go sufficiently up to 6, 7 order, and then go on solving it for first derivative and second derivative. Then you find both f of u and s of u in terms of first derivative and second derivative. Substitute it in this linear combination t equal to h square f of 0 plus h p1 f naught x plus h square p2 f naught xx. When you substitute, you will get This is the derived relationship. When you derive yourself, then only you can come that it is coming out to be this. All right.
Yes, sir.
Now there are so many terms in this relationship T. HQ, H4, this is Sx, this is H4U at x naught plus order H6. I am interested in only those terms whose operator is known to us, either the operator form or U is there. No derivative. I do not want any derivative. So this is the only term. This is one of a term that consists of operator, and this term that consists of U. So these two terms are only useful to us. Other terms are not useful to us because this term consists of third derivative, this term consists of fourth derivative. This is not useful to us. So I am going to nullify it. So if I take coefficient of U third derivative and U fourth derivative 0, and this is possible if you take P1 is 0 and P2 is 1 by 12. With this constraint, with this value of P1 and P2, these two terms will cancel out, will vanish basically. And then you get T coming out to be this. So I have got a linear combination T which is order H6 at this point of time. Can I stop here? If you all permit.
Yes, sir. Yes, sir. We'll continue tomorrow. Next time.
Certainly.